Assalamualaikum. Today our group will be presenting our soil engineering laboratory project titled Soil Stabilization Using Cement Waste. My name is Nurin Aufa. Together with my group members Najwa Hazika and Zanatul Ayun Natasha, we will cover the background and objectives of the study, the methodology and materials used, the experimental results, followed by the discussion, conclusion and the advantages of using cement waste as a soil stabilizer. Without further ado, let's begin with the introduction. First, let me introduce the background of our study. Cement waste contributes to environmental pollution because large amounts are produced from construction activities. At the same time, some natural soils have poor engineering properties and need to be improved before they can be used in construction. Therefore, this study investigates the use of cement waste as a stabilizing material to improve soil properties while also reducing construction waste. The objectives of this study are to compare natural soil and cement waste treated soil and to determine the effect of cement waste on the engineering characteristics of the soil. So the materials used in this experiment are very simple. They include natural soil, cement waste and distilled water. The natural soil acts as the base material, cement waste is used as the stabilizing agent, and distilled water is added to achieve proper mixing and moisture content during sample preparation. Next, I will explain the methodology of our experiment. First, we collected the soil samples from the selected location. The samples were then brought to the laboratory for testing. Then, we prepared the soil samples by removing unwanted materials such as stones and roots. The soil was dried, sieved and mixed with the required percentage of cement waste to ensure a uniform mixture. After that, we conducted the cone penetration test to determine the consistency and strength of the soil by measuring its resistance to penetration. Then, we performed the plastic limit test to determine the moisture content at which the soil changes from a plastic state to a semi-solid state. Using the results from the Atterberg limit test, we calculated the plasticity index by subtracting the plastic limit from the liquid limit. The plasticity index indicates the plasticity and compressibility of the soil. Next, we carry out the standard Proctor test to determine the optimum moisture content and the maximum dry density of the soil. This helps identify the best moisture level for soil compaction. Lastly, we compared the results between the untreated soil and the soil mixed with cement waste to evaluate whether the cement waste improved the engineering properties of the soil. These are the main apparatus used in our experiment. For the Atterberg limit test, we used a cone penetrometer, moisture cans, mixing tools, oven and a weighing balance. And for the standard Proctor test, we used a Proctor mold, rammer, weighing balance, oven and a straight edge. These apparatus we used to prepare the soil samples and carry out the test accurately.
This shows the result of the liquid limit for without cement waste. The liquid limit of the soil was 43.3%. This indicating the maximum plasticity. The soil has a moderate water capacity and moderate compressibility. Next, this result shows the liquid limit for with cement waste. The liquid limit of the soil was 38.5%. This indicating the medium plasticity. The soil can retain a reasonable amount of water before reaching the liquid state. Next, the result shows the plastic limit for the without cement waste. The plastic limit is 26.04%. This indicating that the soil remain plastic until the moisture content decreased to 26.04%. Below this value, the soil becomes semi-solid and start to crack or crumble. Next, this is the result for the plastic limit with cement waste. The plastic limit of the soil is 26.31%. This indicating that the soil changed from a plastic state to a semi-solid state when its moisture content decreased to 26.31%. Below this moisture content, the soil loses its plasticity and begin to crumble when rolled into a 3 mm thread. This is the result for standard Proctor test for without cement waste. The standard Proctor test shows that the soil achieved its highest dry density of 1.66 gram per centimeter cube at an optimum moisture content of 50%. Beyond this point, additional water reduces the dry density due to excess moisture in the soil. Next, this is the result for the standard product test for wheat cement waste. This graph shows that the dry density increased as the water content increased until it reached the maximum dry density of 1.76 gram per centimeter cube at the optimum moisture content of 40.09%. The dry density decreased because excess water filled the soil void and reduced the effectiveness of compaction.
A few moments later.
Now, I will explain the discussion of our results. Based on our experiment, adding cement waste changed the properties of the soil. First, the plastic limit decreased by 4.97%. This means the soil become less plastic and more stable. Next, the maximum dry density increased by 0.1. This shows that the soil could be compacted better, making it stronger and denser. Besides that, the optimum moisture content decreased by 0.96%. This means less water was needed to achieve the maximum compaction of the soil. Overall, the treated soil showed better engineering properties. Therefore, it is more suitable for construction because it is stronger, more stable, and easier to compact. To conclude, the results show that the cement waste successfully improved the characteristic of the soil. Compared to the control soil, the treated soil performed better in terms of stability and compaction. This shows that the cement waste can be used as a sustainable soil stabilizing material. It not only improves soil performance, but also helps to reduce construction waste, making it a more environmentally friendly option. Now, I will explain the advantages of this project. First, this project helped us improve our laboratory skills by carrying out different soil tests. Second, we learned the correct procedures for soil testing and how to analyze the test result. Third, working in a group helped us improve our teamwork and communication skills. Finally, this project promoted sustainable engineering by using cement waste as a recycled material instead of throwing it away. This helps reduce waste and supports environmentally friendly construction. So these are the references that we referred for this project. That is the end of our presentation. Thank you very much for your time and attention. Thank you.
Thank you, everyone! Thank you, Elmar! Go!